Hello dear students. So in today's class we will continue our discussion on Debye shielding. We will try to derive a mathematical expression for Debye's potential, thereby interpreting what is Debye's length. So we will try to derive an expression for Debye length, and then in characterizing plasma or in discussing the various parameters or various properties of plasma, it is very important that we understand what is called as the plasma oscillations. So, we will in today's class we will try to understand what are plasma oscillations, and we will derive an expression for plasma frequency. So, when we are talking about the Debye's shielding, so we have seen that if you keep a positive test charge in a plasma, we have realized that this positive test charge will be surrounded by a cloud of electrons, not just one electron, but a cloud of electrons, such that the effect of this positive test charge will not be realized or will not be felt at any point beyond this cloud. So, we defined this particular typical length scale as lambda d, which is also called as the Debye's length. So, to define Debye's length, it is the length scale over which plasma tries to shield the effects of or the electromagnetic effects of a charge. So, beyond this distance, the electromagnetic effects or the charge's influence will not be felt. Okay. So, basically when you keep a test charge in a plasma, generally what happens, in the beginning it will start attracting the electrons. Okay. Now, from here onwards, what we can say is that, let us say the number of electrons and number of ions are equal. So, number of electrons is equal to number of ions macroscopically. Macroscopically it is equal, but when we were defining what is quasi-neutrality, we also made a mention saying that plasma allows the possibility of local or tiny deviations from the electrical neutrality only to the point that the electrostatic potential energy that arises due to the charge separation is roughly of the order of the kinetic energy of the electrons. So, the basic idea was very simple. Before we get here, it is very important to understand the neutrality of the plasma as a whole. So, if you have charge accumulation anywhere in the plasma, it will always be such that an electric field is generated by this charge accumulation or charge separation, and electric field will always try to compensate, or let us say we will always try to create charge movement, allow charge movement in the opposite direction of electrons. Let us say electrons will move opposite to the direction of electric field, and the movement of these electrons is such that it will try to nullify the existing electric field. But then we realize that these electrons in an attempt to neutralize the positive ion, they will always overshoot the mean position, and a restoring electric field is set up in the opposite direction. The role of this restoring electric field is to bring back the electron to the neutral position. In the process, there will always be oscillations, right? Now, when you look at the plasma is considered electrically neutral. That means the total number of electrons is equal to the total number of ions. And if you talk about the charge, let us say total positive charge in terms of number of electrons is equal to the total negative charge. In total positive charge in terms of number of ions is equal to total number of negative charge in terms of electrons. But plasma, being an electrical conductor, is not just a gas with molecules. So, plasma should also allow the possibility of Coulombic interactions between various constituents of the plasma. That means that plasma is neutral macroscopically, but microscopically in small regions of plasma, charge accumulation may always take place, right. Now, if you allow the possibility of a positive ion here in the plasma, what we can realize is that within some time it will start attracting the negative ions, and they will form a cloud around the positive ion when you keep a positive test charge, right. Now, what we are going to find out is, let us say, we will be interested to find how this cloud is able to shield the this electric field. So, if you keep a positive test charge, the electric field due to this positive test charge by the means of Coulombic interaction should always be felt, or can always be experienced at any point in the plasma, right. Any point in the plasma should be able to experience this positive test charge. But what generally happens is, due to the concept of Debye shielding, the electrons will surround the positive ion up to a particular distance, and beyond this particular distance, electrons or any other charge will not be able to experience this positive test charge. So, this is the means by which plasma shields out the external electric fields. Okay, so that means there is only up to a limited spatial extent the external electric field's influence can be felt in the plasma, not the entire plasma itself. Okay. Now, the spatial extent to which the electric field's influence can be felt can be called as the Debye's length. Now, we are going to derive a relation for Debye's length, and we are also going to see how the potential of a positive test charge will look like inside a plasma, right. Then the question really comes, I mean, what are the parameters over which this Debye's length will depend? Will it depend on the mass of electron? Will it depend on the number of charged particles per unit volume in the plasma? Will it depend on the temperature? Will it depend on any other property of the plasma, let us say, for example, right. Now, we will try to see all of that. Okay. So, for example, what we can do is we can take let us say we can take plasma, and we have a positive test charge in the plasma, right. Now, so we are saying the cloud of electrons will be surrounding the plasma, right. Now, at let us say when at t is equals to 0, when you keep the positive test charge, I can write the potential due to this positive test charge at any distance as simply 1 by 4 pi epsilon naught q by r. So, what is the nature of this potential? The nature of this potential is simply Coulombic. And what is the range of this Coulombic interaction? It is infinite. I mean, at any point in space should be able to feel the influence of this test charge, right. Now, when you allow sufficient amount of time as t increases away from 0, as t increases, we have to find the nature of this potential. How will this potential appear? Now, to begin with, we are saying that the potential due to this positive test charge cannot be felt after a particular distance, right. We are saying that. Now, we have to see if we allow sufficient amount of time for this charge accumulation and the formation of cloud to occur, we have to find out the empirical form of this potential after sufficiently large amount of time. So, how will this potential change, deviate away from the Coulombic potential is going to be the topic of our discussion, right. Now, let us say, so now, so to ease our calculation, we say that the mass of electron is immensely small when compared to the mass of ion, which means that the velocity of electrons is very large when compared to the velocity of ions, right. Why are we making this assumption? We are making this assumption to say that the ions are not moving, ions are at rest, I mean, so the ions are not moving, so they constitute a simple neutralizing background. At t is equals to 0, number of electrons in the vicinity of, let us say, the test charge is equal to the number of ions, just to begin with. Let us call this concentration as M naught. As time progresses, as t increases, let us say t increases, what will happen is number of electrons in the vicinity of the positive test charge will be slightly greater than number of ions, right. If it is the case, then what we can do is, so within this sphere of influence of positive test charge, we can say that the total charge accumulated, let us say, is or the total charge density, for example. So, the total charge density is number of electrons minus number of ions times the charge, right. So, n is the number of particles per unit volume and q is the charge. So, since the number of electrons is more in the vicinity of this test charge, the resulting charge density can be written as rho is equals to Ne minus Ni times q. Now, we very well know that del dot E is rho by epsilon naught and E is equals to minus del phi. So, this charge accumulation, if at all, if there is a charge accumulation, there has to be a resultant potential due to that particular charge accumulation, and any particle should be able to experience this particular potential. And if there is a particle which is experiencing this potential, the potential energy, if phi is the potential energy that will come out of this configuration is just E phi, where E is the charge of the particle and phi is the potential over which it is accelerated. Okay. Now, substituting this into this equation, what we can do is we can simply write del square phi is minus rho by epsilon naught, right, which means that del square phi is equals to minus Ne minus Ni into q by epsilon naught. So, now we know that within this small sphere of influence of the positive test charge, there is a charge accumulation. The magnitude of this charge accumulation is known, the charge density that is available in this region is known, and the resulting potential is given the name of phi. Now, our objective is to solve this second order differential equation and see how the form of phi supports our argument saying that the potential will not stretch beyond Debye's length. Okay. Now, for simplicity we say that, so phi is in the spherical polar coordinates r theta and phi, right, and the positive test charge is situated at r is equals to 0. So, this is the position of the positive test charge, simple, right. Now, so in order to do this, let us say, so what we should know is, we should know how Ne and Ni will look like in the presence of this potential E phi, and there is also a thermal energy which is attributed to the electrons by the virtue of temperature, and in addition we should also be knowing how the velocities of the electrons or ions are distributed, right. So, that means that n is the number of electrons, Ne is the number of electrons per unit volume. So, how is this number of electrons per unit volume going to change as a function of r away from this positive test charge? Because there is a potential, the electrons will experience a potential energy. Because there is a temperature, the electrons' thermal energy will be decided, and these thermal energies are going to be distributed as per their velocities, right. Now, let us say for example, so what we can simplify is that, let us say, so if n if at very far distance, Ni at infinity, so that means away from the vicinity of the test charge is n naught, and Ne at infinity is equals to n naught, right. So, not in the vicinity of the test charge, it is natural to expect that these concentrations will be equal. It is only in the vicinity of this test charge things are not equal, right. Now, let us say we say that, so they are following Boltzmann's law. So, if their distribution is according to the Boltzmann's law, we can say that, let us say we should have a distribution function now. So, their velocities are following this function a times exponential minus of half mv square. Half mv square is the kinetic energy of the electron, let us say, of the particle, plus E phi is the potential energy, which is by the virtue of the potential due to the positive test charge, right. So, this entire factor becomes a probability factor. Right. Now, how do you get the number density from this probability factor? You just integrate this between minus infinity to infinity f v f u dvx, dvy and dvz. Right. So, we will realize that n is proportional to e to the power of minus e phi by kbt. So, we can write number of electrons is equals to n naught exponential minus of e phi by kb t, which is equals to n e is number of electrons per unit volume, is since e, the charge of electron is to be taken as minus e, we will write that e phi by kb t. So, it is more appropriate if you write kb te, right. So, similarly you can also write n I is equal to n naught exponential minus e phi by kb t I, right. Now, so we are trying to solve del square phi is equals to minus q times n e minus n I divided by epsilon. We are trying to solve this, right. So, we can substitute, let us say this as equation A and this as equation B. We can also say that number of ions, since they are just constituting a background, but not are distributed as per their velocities. Let us say they are not moving anyway. So, the effects of potential being taken away, we can say that the number of ions is simply n infinity or n naught. We can also say that. So, if you say that, we will have to solve this second order differential equation to be able to get the functional form of the potential. So, del square phi in the spherical polar coordinates is to be written as 1 by r square dou by dou r of r square dou phi by dou r plus 1 by r square sin theta dou by dou theta of sin theta dou phi by dou theta plus 1 by r square sin square theta dou square phi by dou phi square is equals to 0, not is equals to 0. So, this is equal to again minus E times n e minus n I divided by epsilon naught, right. So, let us say the potential phi is symmetric in theta and phi and varies only in r. That means, so derivatives with respect to theta and derivative with respect to phi are to be treated as 0. So, what we will be left with is 1 by r square dou by dou r of r square dou phi by dou r is equals to minus E by epsilon naught times n e minus n I, right, which we can write as 1 by r square dou by dou r square dou phi by dou r is equals to minus E n naught divided by epsilon naught into 1 minus exponential E phi by kb t, or more we can also write. So, since now phi is just a function of r, so we will write 1 by r square dou by dou r of r square dou phi of r divided by dou r is equals to right n e minus n I, right. So, it's going to be this minus 1. Okay. So, this is going to be minus 1. So, now if you substitute 1 by r square. So, if you say that E phi is much less than kBT, so if the potential energy is much less than the thermal energy, we can write r square dou phi of r divided by dou r is equals to minus E n naught by epsilon naught into 1 plus E phi by kBT minus 1. So, what we will have is 1 by r square dou by dou r square dou phi of r by dou r is equals to minus E square n naught phi by epsilon naught kb t. So, here again phi is a function of r, right. Now, if you substitute the electron's charge being negative, we can write this equation as 1 by r square dou by dou r of r square dou phi by dou r is equals to E square n naught by epsilon naught kBT to phi of r. So, we can write this as a constant as 1 by lambda d square to phi of r. So, how did I define lambda d? Lambda d is epsilon naught kBT divided by n naught E square, right. So, I have this second order differential equation. What is this equation? This is 1 by r square dou by dou r of r square dou phi by dou r is simply 1 by lambda d square phi of r. Now, the solution of this differential equation is going to be the functional form of the potential, right. So, the solution looks something like this. Phi of r is simply 1 by 4 pi epsilon naught q by r into e to the power of minus r by lambda d, right. So, this has two parts actually. This has, let us say we call part 1 and part 2. So, part 1 is Coulombic potential. You see it clearly, just 1 by 4 pi epsilon naught q by r. The part 2 is an exponential part, Now, how do we understand the effects? I mean, what we have been able to do is we have been able to get the functional form of the potential that exists within the if you have a positive test charge and if this line indicates the presence of the electron cloud, we have been able to establish how does the potential vary with respect to r within this sphere of influence inside the plasma, right. So, what it means is that if you have plasma, so how does r vary? I mean, if you do not have plasma, potential is simply Coulombic in nature, which is just kq by r. But if you have plasma, you have the additional appearance of this particular this particular exponential part, right. So, this is very important. I mean, this will decide how the potential within the Debye sphere will vary with respect to space, right. So, ultimately what we have derived is phi as a function of r, of course, and so this is part 1 and part 2. So, I mean, you see that part 1 is 1 by r dependent and part 2 is exponential minus r. So, both of them are decays, 1 by r decay and exponential minus r decay. So, 1 by r is kind of slower in comparison to exponential minus r. So, this decays much faster. So, exponential decays much faster than the 1 by r decay, right. Now, let us try to understand the more important features of this particular potential, let us say. So, we have defined phi, we have been able to derive is 1 by 4 pi epsilon naught into q by r exponential minus r by lambda d. Let us say, let us observe this, so this is part 1 and this is part 2. So, when r tends to 0, that means in the closest proximity of the test charge, when r tends to 0, which is the closest proximity of the test charge, what will happen? So, the exponential term simply becomes nearly equal to 1, right. But the so, at the closest proximity of the test charge, the exponential term becomes 1 and the Coulombic term becomes very large. So, let us say we see the Coulombic potential becomes very large. So, what do you infer? So, within the in the closest proximity of the test charge, the potential is clearly Coulombic in nature. So, R tends to be very small, so potential tends to be very large, right. So, the potential is just very large and the nature of potential is just Coulombic in nature, right. When R increases, let us say when R increases, what happens? When R increases, this particular part, the second part will start becoming smaller. So, Vc will decrease, right, and exponential will also decrease when R increases, right. So, how does it decrease? Let us say for example, when R is taken as lambda d, okay, when R is equal to lambda d. So, the potential is phi of R. So, if it is just Coulombic potential, we can simply say that phi of R is 1 by 4 pi epsilon naught q by lambda d. I mean, lambda d is a limit, is just a distance, this is lambda d. So, here everywhere here the potential is varying as 1 by r. So, the potential is decaying as 1 by r here. When lambda d becomes, I mean, so the potential should just be 1 by q by 4 pi epsilon naught 1 to 1 by r d. The potential should be just that. But due to the additional second term, so this second term was just 1 when it was very close to the positive test charge. So, here when r becomes equal to lambda d, it simply becomes 1 by E. So, the potential, is just potential at lambda d into 1 by E. So, what you can say is that, so when at the Debye's length, the potential suddenly drops to 1 by Eth of the potential which should be, which should be present at lambda d, right. So, what happens even after that? So, even after that, so the decay will be faster. So, if you cross the limit of lambda d, the potential will become even more, let us say. So, the potential is 2 lambda d, let us say phi of r, then now becomes, let us say 1 by 4 pi epsilon naught into q by 2 lambda d into exponential minus 2, right. So, this is even a smaller potential than this, right. So, what you observe here is that Debye's potential, or so Debye's potential is just, I mean, the potential inside this Debye sphere is not varying as 1 by r, but is varying 1 by r up to a certain limit, and beyond this certain limit it is falling even more faster. So, the potential should ideally be, let us say, should be like this, and then now the potential is dropping suddenly like this, right. Now, let us see if we draw it more carefully. So, now the potential is, if you take r on the x axis and phi of r on the y axis, it will look something like this. It will look something like, so this is the 1 by r potential, and suddenly it becomes exponential and decays even more faster. So, this decay is Coulombic, and this decay is exponential. So, this is 1 by r decay, and this is exponential minus r decay. So, you obviously you can see that the exponential decay is very fast in comparison to the Coulombic decay. So, what does it say? I mean, it says that if you have plasma, I mean, this kind of supports our understanding of Debye shielding anyway, right. So, how does it support? It supports in the sense that if you have plasma, then the influence of this positive test charge propagates by the means of creating a potential. Generally, in electromagnetics, we have learned that the range of the Coulombic potential is infinite. It extends, I mean, there is no stopping. But if you have plasma, the potential will not stretch beyond a certain limit, and this certain limit is called as the Debye's length. So, in terms of this potential, we have been able to realize that up to this Debye's limit, the potential is simply Coulombic. So, that is the natural order of things. So, but when you cross this, when you are just approaching the Debye's length itself, the potential suddenly drops to 1 by e of the original value. So, this is the beauty of Debye shielding. So, what we can conclude is that, so Debye shielding is the mechanism by which plasma shields out the electromagnetic effects of electric fields on the plasma. So, if you keep a test charge inside, the electric field that is created by the positive test charge is shielded out for the rest of the plasma, and if you keep an electric field outside, it will do the same thing again. The plasma will create a mechanism by which the effects of this electric field are shielded out for the rest of the plasma. The depth up to which the electric field will penetrate into the plasma is called as the Debye's length. Okay. Now, more importantly, if you look at the expression of Debye's length, there are a few very important conclusions that are to be drawn. So, if you look at the expression lambda d is the Debye's length, it is simply epsilon naught kb t by n e square, right. So, what it says is that, so what we can realize from this is that, so as the temperature increases, the Debye's length will increase. So, if you have a plasma which is very hot in nature, it will have a larger Debye's length. Okay. That's a very important conclusion. We will try to understand how does it, I mean, why does it vary like that. If you have more, so the second thing is, if you have particles per unit volume, as the number of particles per unit volume increase, the Debye's length will kind of decrease, right. So, these two are the main, otherwise the rest of the things are just constants, right. So, Debye's length will not depend on the mass, Debye's length will just depend on the temperature and will depend on the number of particles, charged particles per unit volume. So, let us look at this. What does it say? I mean, it says that as there are more number of particles in a given plasma, the Debye's length will be smaller. I mean, it is kind of contradictory to our idea that when the particles are more, the Debye's length should be larger. But what it means is that as the number of particles are more, it takes, I mean, the available particles to neutralize a positive test charge are more in a given volume. So, within a small volume itself, then there are more number of electrons present. So, it will not take much of the space for the shielding to happen. So, in a denser plasma, the positive test charge or the electric field is shielded in a very minimal extent of space. So, this is the basic understanding of Debye's length. Okay, so now we have one more topic for discussion, which is called as the plasma frequency. So, we have seen how the plasma tries to restore or maintain electrical neutrality So, plasma oscillations are the means by which plasma maintains electrical neutrality. So, let us say how it let us see how it does it. Plasma frequency. So, plasma frequency is a very fundamentally very important parameter. So, plasma frequency is let us say for example, when you look at the ionosphere, let us say ionosphere has nearly 10 to the power of 12 electrons per unit volume, right. So, what it means is that due to the number of charged particles present, there is a frequency associated with the plasma. So, what is the idea of frequency is that let us say if you have plasma and if you displace an electron away from its position and create a charge density somewhere, this charge density will try to create an electric field and such that the displaced electron has to be restored to its original position. So, this is the idea of maintaining equilibrium, right. So, at any given temperature, now very important thing is at any given temperature there is always an amount of thermal energy that is associated with the particle. So, particle inherently has some energy. So, because of which it is moving around. So, now if the electric field is making the particle to go in a direction, in addition to the electric field, the potential energy created by the electric field, the particle also has some energy by the virtue of its temperature. So, these two things are there with the electron, right. Now, what happens is the electron of course will try to go back to its original position, but in the process it will overshoot the position because of the inertia. The particle has some mass, so it has some inertia. So, it will always overshoot the position because of its velocity, right. When it overshoots, again there is a restoring electric field that is set up, and this restoring field will just try to bring the electron back to its position. So, this to and fro movement will create an oscillation. We will be interested to find out what is the frequency of these oscillations, and this frequency of the oscillation is a characteristic of the plasma itself. So, this frequency will be dependent on the characteristic or on the number of particles that are present in the plasma itself. So, every plasma is characterized by its frequency. Okay. So, in this example what we will do is we will try to derive the plasma frequency. Okay. So, let us consider an example. Let us say that there are equal number of electrons and ions in the plasma. Let us say by some mechanism we have been able to displace all the electrons away by a small displacement of delta x. So, I have been able to, by some mechanism I have been able to displace all the electrons onto a slab by distance of separation delta x. So, naturally all the positive charges are separated from the negative charge separation, negative charge accumulation by this small distance delta x. Now, this arrangement does look like a simple parallel plate capacitor, right. So, what we have to do is we have now we have to find out what will be the frequency associated with the restoring forces in this particular picture. Okay. Now, let us say if there is a slab which is on which all the electrons are accumulated, we can write the charge density of this slab as Q by A, which is minus E times the number of particles per unit volume times delta x. So, this is the number of particles per unit volume. So, you are getting sigma is the charge density, the surface charge density on this plate. So, Q by A, Q is the charge, A is the area, right. So, if this is the surface charge density, the resulting arrangement leading to the formation of an electric field is simply sigma by epsilon naught, which is equals to E n naught delta x divided by epsilon naught. So, this is for the electrons, and for the ions it is E n naught delta x, right. So, the direction of electric field is just in the direction of electric field is in this direction, and the movement of electrons, so this is E, and the movement of electrons is in this direction, right. Now, we can use the Newton's second law of motion, let us say. So, what is it? F is equals to ma. If there is an electric field, the amount of force that is experienced by the electron is F is equals to Eq. right. So, now that means that E times minus E is equals to m A minus E times E n naught delta x by epsilon naught is equals to m E d square delta x by dt square, which means m E. So, d square delta x by dt square. So, this is m A, this is d square delta x by dt square is the acceleration times mass is equals to the force, which is electric field times the charge. We have already got the electric field here, right. So, is equals to minus E square n naught delta x divided by epsilon naught. So, this looks like a simple harmonic motion. We can write d square delta x by dt square is equals to minus omega p e square into delta x. So, this is the angular frequency. So, that means that omega p e is equals to e square n naught by m epsilon naught. So, this if the particles are displaced and if the particles are executing something called as a simple harmonic motion, the angular frequency of these motions should be of this order. So, let us say, so this is now if you want to calculate the frequency. So, the frequency of electron plasma frequency is simply this, which is E by 2 pi into square root of n naught by m epsilon naught. So, FPE is 1.6 10 to the power of minus 19 divided by 2 pi times n naught can be anything times 9.11 10 to the power of minus 31 times 8.85 10 to the power of minus 12, which will reduce to 9 times square root of n naught hertz. So, this is the electron plasma. This frequency is called as the electron plasma frequency. So, what are the features of this plasma frequency? Plasma frequency depends on the mass and plasma frequency depends on the charge, right, charge per unit volume. So, plasma frequency, I mean if the particles are more denser, the plasma frequency is going to be smaller. Now, again here we always say the electron plasma frequency, but the ions are massive, they cannot move. So, it's the same thing that we say again, right. So, this is something about the Debye shielding and plasma frequency. So, now Debye shielding has given us a length dimension lambda d, and the plasma frequency has given a frequency term which we call as FPE. So, in addition to this, so if we define what is called, we can also define using lambda d as the length dimension, we can also define a parameter called as capital lambda d, which is called as the plasma parameter, What is the importance of this plasma parameter? So, if you have a sphere of radius lambda d, the volume of that particular sphere is going to be 4 by 3 pi lambda d cube. So, this is the volume. So, the number of particles in this spherical volume of radius equal to Debye's length is going to be the plasma parameter. So, n is the number of particles per unit volume, you are multiplying with the volume itself. So, which will give you the number of particles which are present in a sphere which has the radius equal to Debye's length. So, plasma parameter is a very important characteristic of the plasma. So, depending on the plasma parameter, you can say or quantify what type of plasma it is, what could be the effects of this plasma, and so on, right. So, now like I said before, so every plasma differs greatly in comparison to any other gas. So, plasma is of course a gas, but with charged particles. So, the charged particles are enough in number so that we can take into account the electromagnetic effects. Okay, so, this is going to be the conclusion about our discussions on the introductory plasma physics. So, these topics will be very much useful for you to appreciate the various aspects of ionosphere, how the ionosphere responds to various types of solar energy input, and how the ionosphere is coupled, because ionosphere is charged entity, how the ionosphere is coupled with the magnetosphere of the earth and the magnetic field of that is created by the sun. Okay. Yeah.